Hello students.
Good morning, sir.
Good morning everyone. So now I'll continue with the second chapter of the electromagnetic theory, magnetostatics. The second chapter is magnetic field produced by magnetic materials. It is called a material media. And now we'll take up what is called as magnetic circuits. Now when we say electric circuit, all those circuits which we come across in the current electricity, they are electric circuits. Essentially, they will have wires, resistors, capacitors, inductors, then the cell, current is flowing through that. So these are the electrical circuit. Now let us see what are the magnetic circuits. Now in the magnetic circuits, there are circuits means a closed path, the closed path made up of magnetic field lines. Magnetic field lines, group of magnetic field lines is called as a magnetic flux. And we take it as a magnetic circuit because the magnetic field lines produced by any source always forms the closed loop. Example, a current carrying wire. Around that, the magnetic field lines are a form of circles. So, by any other material also, the magnetic field lines always form the closed loops. So that means in general magnetic flux forms a closed loop. Now in case of the bar magnet, see when we consider a bar magnet, suppose you take a bar magnet, the north pole and south pole, see the magnetic field lines, what happens is these magnetic field lines inside they are in a certain closed path inside, but outside they spread to the large distance. So inside they are in a specified region, but outside you will find that the separation will be more and more, and they will be separated to the large extent. Same thing for the solenoid. Solenoid also same thing. Solenoid carrying a current. Now same thing. It is a magnetic field line similar to the bar magnet. But if you consider the toroid, if you consider the toroid like this, if you consider a toroid, you will find that in this region the magnetic field is zero. That means there are no magnetic field lines. Outside the magnetic field is zero. That means there are no field lines. So magnetic field lines are only inside this region of the toroid. So field lines will be there. So now what happens is, and it will form a closed loop. Here it forms a closed loop. Everywhere it forms a closed loop. But what happens is, unlike this bar magnet or a straight solenoid, in the toroid, the magnetic field lines are confined to the specific region, well-defined path. Now, the circuit made of these magnetic field lines, that means magnetic flux, as in the case of the toroid, that is called as a magnetic circuits. So magnetic circuits contains the magnetic field lines, that is magnetic flux. But those magnetic field lines should be confined to that well-defined path. So in the case of the solenoid, it is in the well-defined path. Here it is not in well-defined path. It is spread to the large extent. So one of the example of the magnetic circuit is a toroidal winding. See toroidal winding. Now in the toroidal, see the toroidal winding can be done over a ring. So you can take a metal ring. It should be metal ring, essentially ferromagnetic, and over that you can wind the wire like this. So there also what will happen is the magnetic flux is inside this metal ring. So this toroidal wire winding or iron ring need not be iron, it can be any other ferromagnetic material. is also form a magnetic circuit. Then now here in this in the toroid, see in the toroid there can be a ring, but for that ring there can be a gap, so air gap. Now this ring may not be of the same material. Part of that may be a soft iron, part of that will be the maybe the nickel, the part of that can be the cobalt, ferromagnetic material. So this ring may have the gap, and it may be made of the different type of the ferromagnetic material, that of the different properties. So we can consider when you pass a current, the magnetic flux will be confined to this region, in this circular region. And but we can consider here the magnetic circuit made of different types of material in series: air gap, iron, nickel, cobalt, and so on in series. So just like current electricity, your series combination. So in the magnetic circuits also there is a series combination, but here series combination may be made up of the gap and a different ferromagnetic material. So this is what are called as a magnetic circuit. Next, just like say in the case of the electric circuit, we have the basic equation like this: V equal to IR, voltage equal to current into resistance. This is a basic circuit, Ohm's law. So basic circuits in case of the current circuit is V equal to IR. V is the EMF. Uh, Essentially, V is the EMF, current into the resistance. Now we want to find a similar expression in case of the magnetic circuit. So that is the basic magnetic circuit equation. Now let us consider a general series circuit. So here series circuit is of the magnetic circuit of several material. That means that normally the toroid we take, that ring inside may be made of the different ferromagnetic material, and there can be gap surrounded by the toroidal winding of capital N turns current. Then to that we apply the Ampere circuital law. We apply Ampere circuital law, and Ampere circuital law is this integral law. Actually, it is vector H dot vector dl equal to Ni. N is the total number of times the current is entering. Current is entering that Amperian loop. See for the toroid like this, we take the loop like this, a closed path. We take a closed path, imaginary closed path, that is the Amperian loop. Then I is the current flowing in that toroid, and N is the total number of turns. So what happens is this circular path, Amperian path which you have considered, for every winding the current will enter and it will come out for every winding. So there are n winding. So n time the current will enter and come out. So that is that Ni. We write it as I suffix E, enclosed current. In the Ampere circuital law, that current I is a total current. How many times that current has entered that Amperian loop. So the total is Ni. Then see here the dl, length of this Amperian loop. So direction of dl is a tangential at each and every part of this circle. Then vector h is also tangential. So angle between them is 0. Angle between h and dl is 0. So h dl cos 0. Cos 0 is 1. So that's what we heard. I simplified and written here that line integral of h dl. Actually it is vector h dot vector dl. But vector h dot vector dl is h dl cos theta. So theta here is 0 because direction of h and direction of dl is a tangential for that Amperian loop. So the angle is 0. Both are tangential. Then we make use of this. The magnetic induction is proportional to the magnetic intensity. Constant of proportionality is permeability. mu. Then we use this phi equal to BA. So phi equal to B, actually BA cos theta. Theta here is 0. Cos 0 is 1. Because see, for every loop of this, area vector is perpendicular to that. And vector B is also perpendicular to the loop. So angle between them is 0. So BA cos 0. So BA. Then we substitute B equal to mu A, mu H. B equal to mu H. And when you simplify, you get H equal to phi divided by mu A. We substitute in this equation 1. So you get this equation. Then we take that phi outside. We take phi, in fact, phi mu by A, they are all constant, but only phi we take outside, and we keep remaining thing inside. So now we have written this as flux into this integral equal to Ni. Now we will compare it to the equation in the current circuit. In the current circuit, say IR equal to V. V here is EMF, electromotive force. This V is the EMF, electromotive force. So here, if you compare this equation, this quantity, see this quantity and this quantity is similar. E and Ni, that is similar. So we name it as, see, this just like in the current electricity, we have electromotive force. In the magnetostatics, we call it as a magnetomotive force, MMF. Just in comparison, we name it. So we are writing this in comparison with the electricity. MMF means magnetomotive force. There's no much meaning in that, but in comparison with the electricity, we are writing it. So this is the electromotive force. Then I into R. So this corresponding to that I, current. See, current. In the current electricity, current is there. And in the magnetic circuit, what is there is the flux. See, this the flux is circulating inside this solenoid. It is circulating. So it is like a current. So in the current circuit, it is a current, and in the magnetic circuit, it is a flux. So that means the remaining part is like a resistance. It is like a remaining part is like a resistance. So in the magnetostatic, we call it as a reluctance. It is called as a reluctance. Reluctance R. We write it as R. Actually, it is written in the Greek symbol R. So it is more it is written like this. The more often it is written like this, Greek symbol. I use here the Roman symbol only, alpha letter R. So it is integral of 1 by mu A dl. And then we can write this phi, that is the flux as this quantity is that magnetic motive force, and this quantity is that reluctance. So the flux equal to magnetic motive force divided by reluctance. So this is the equation, similar equation. Now this is what is called the basic equation of a magnetic circuit. So all these things we have done in comparison with the current electricity. Then next we consider a magnetic circuit, another magnetic circuit. So earlier what I have considered magnetic circuit, example which I have taken is a toroid with the iron ring inside. For that iron ring there may be a gap, and that iron ring may not be of the same material, they may be of the different ferromagnetic material. So now here we consider another magnetic circuit. Magnetic circuit means where magnetic flux is confined to the specific region, well-defined path. It should be well-defined path. It is not spreading to the infinity. If you take a single bar magnet, what happens is the flux will tend everywhere, will be there up to the infinity. But in magnetic circuit, that flux has to have a certain well-defined path, definite path. So what do we consider here? As we have in this what is called the permanent magnet circuit. See that PM is a permanent magnet. So this is the permanent magnet, bar magnet. This is a bar magnet. If you take a bar magnet alone, then its field line, that is the flux, is in the indefinite region. It will be spread all over. Up to infinity it will go. Now, next what is done is, we put here, touching this permanent magnet, we use here material, a soft iron, ferromagnetic material. So this part, see this part and this part is a ferromagnetic material, and there's a gap here. This is the gap. So there is a gap. So now, because of this soft ion, what happened is this flux produced by permanent magnet will not go outside. It will be confined to the ferromagnetic region. The property of the, I mentioned it in the previous part, that ferromagnetic material, what happens is it confines it has a high permeability, very large permeability. So it will try to take all surrounding magnetic flux inside it. So because it has large permeability, so inside there will be large flux. So whatever the permanent magnet producing the flux will pass through it. Now if this gap is very small, then what will happen is it will cross this gap and it will get into this part of the soft ion, and then this flux will get circulated. So now this flux will not go outside. 99.9% of the flux will be in this region. It will be circulating in this region. Almost 99.9% of that. A small amount may go outside. So now this is the magnetic circuit. So what we have drawn here, a permanent magnet, soft ion material, two parts are there, gap. It is a magnetic circuit. Now for this magnetic circuit, we will apply the Ampere's circuital law. So we will apply the Ampere's circuital law to flux path of the permanent magnet. It is this line integral of vector h dot vector dl equal to 0. So it is equal to 0 here. This is equal to 0. Now this is the line integral of h dot dl. So now what we will do here is we will split this integral into two parts. See now for the closed loop, it is a closed loop. Closed loop contains the permanent magnet, this part of the soft ion, gap, and the soft ion. So now what I will do here is I will split this integral for two parts. One part for only permanent magnet and other part for the remaining part of this magnetic circuit. So first part, it is going from this A, to this B, up to this is one part. So integral, see here, integral vector h dot vector dl A to B, that is part. Then for the permanent magnet, we write it separately. So plus B to the permanent magnet to A. So B here, say the B here is a part of that permanent magnet to A, and that is equal to 0. So the first term, what I have written is of the soft ion which is there and the gap, and the second term which is written is of the permanent magnet. Then what we do here is vector h dot vector dl, h dl cos theta. Theta here is 0 because direction of element will be same. So angle is 0. Here also everywhere what happens is the dl is tangential to that field line, and h will be also tangential to that line because b is tangential to that field line. So angle between them is 0. So they are parallel to each other. And we take the second term on the other side, and that second term become equal to minus. So we get like this. Then as we have done in the previous part, we'll substitute this as we have done in this one, h equal to 1, that phi h equal to phi by mu a. We get it using this, b equal to mu h. So phi equal to ba, b equal to mu h. So the h equal to phi by mu a. That's what I have written. Phi I have taken outside, just write in that earlier form. And that is equal to minus integral h dl. So now here you will find that here it is a loop, but here it is not loop, it is a part of the loop. So here it is a loop integral, closed path. Here it is a half part and here another part. Then the magnetic flux is continuous throughout the entire circuit. This flux is continuous. So the flux is B into Bm into Am. This is what we write. Bm is a magnetic field. See, magnetic field in the permanent magnet, and Am is the cross section area of the bar magnet. So the magnetic flux will be there over the cross sectional area of this permanent magnet. So phi equal to Bm Am. That's what I have written. And cos 0 it is actually. Bm Am cos 0, because at a pole the field will arise perpendicular. The area vector is also perpendicular. So both of them are parallel to each other. So angle between vector B and vector A is 0. So cos 0 is 1. That's what we write. Then we can write here on this. See, we can write only for a permanent magnet as minus HM LM. So minus HM LM. So we take that average. That HM is average magnet and LM is the length of the magnet. So we take it that H is almost constant. H is constant because in the permanent magnet H will be constant. The same magnet. Each and every point H will be constant. Then integral of dl is the L. L is the length of the magnet. So here what you return. So this part minus sign is there. So this is minus sign is there. Then H is constant, but that is H in the permanent magnet S suffix M, and L suffix M is the length of the magnet. Integral of dl will be L, and L will be length of the magnet. And on this side, this phi is Bm Am, as you have written here, and that this part we write it as that reluctance. So R suffix M is a reluctance. So we get this equation. We get this equation. We get this equation, and this Bm and Hm can be found by solving the equation simultaneously. You have to use the hysteresis curve. You have to use the hysteresis curve for this soft ion. Then by using that, we can find out. So that's the way to calculate. We are not calculating that here. It's not required for you, but we can find it. So this is the magnetic circuit containing the permanent uh, permanent magnet, and this completes with the chapter. This completes with the chapter. So next what we'll be doing is we'll start with the third chapter. So third chapter we'll be starting, and I'll just tell you I'll start it tomorrow, day after tomorrow. So tomorrow I'm not taking the lecture. On the Wednesday I'll be taking the lecture. So I'll start with the next chapter. You can read it before studying the class. You can read it. So chapter 3 is about the microscopic theory of the magnetism. That means, see, now so far what you have seen in the second chapter, how the magnetic field is produced by material, overall material. How the magnetic field is produced by the given material. But actually what happens inside that material? Inside that material what happens? So that means inside the actually the magnetic field is produced because of the atoms circulating electrons in the atom. So it happens at a microscopic level. So that is called as the microscopic theory of the magnetism. And the as I mentioned in the second chapter that magnetism is of the three types: dimagnetism, paramagnetism, and ferromagnetism. So three types it is: dimagnetism, paramagnetism, and ferromagnetism. Now we will see actually how the dimagnetism is produced. Why material is dimagnetic? We will take into account the atom, electrons which are orbiting, or why the given material is a paramagnetic, or why the given material is ferromagnetic. So that's what we are going to see in the third chapter. So third chapter will be entirely studying dimagnetism, paramagnetism, and ferromagnetism. So that I will do it day after tomorrow. Tomorrow I am not taking the lecture. I will be taking the lecture on the Wednesday at the same time, and I'll stop here. Thank you very much.
Thank you, sir.
All right, welcome.